Somewhere in the labyrinthine astronomical archives, buried in a digital folder among countless other points of light, there exists a single photograph of an object capable of sterilizing Earth. For 7 years, it bore a label that was a masterpiece of cosmic irony: minor planet, no threat. This was Bernardinelli-Bernstein, a comet with the physical breadth of Florida, a frozen leviathan holding 1,000 times the mass of every asteroid we currently fret over in the inner solar system combined, and a girth 5 times larger than the rock that ended the age of dinosaurs. Astronomers saw it. Their telescopes captured its light with perfect clarity. Their algorithms dutifully logged its position. The failure was not of sight, but of comprehension. It presented no fiery tail, no hazy coma, just a stark, solitary pinprick of reflected sunlight, indistinguishable from a harmless chunk of frozen debris minding its own business in the deep, dark quiet. And this is the thought that should whisper at the edges of your consciousness tonight as you look up at a seemingly peaceful sky. How did we miss it? How does something so monumentally vast, a celestial object that would render every deflection strategy humanity has ever sketched on a whiteboard utterly pathetic, simply slip through the cracks? Stay with me. For the next 2 hours, we will unravel how the King of Comets exposed the most dangerous assumption in astronomy: the arrogant belief that we would see it coming. This cosmic filing error has you questioning what else lurks in the data. Hit subscribe. You'll want to be here when we dive into the other ghosts hiding in plain sight. Leave a comment. Tell me where in the world you're watching from, your time zone, and whether you think our planetary defense is ready for what the Oort cloud might throw at us next. Or if we're still, as we'll see, flying utterly blind. This was the mistake that happens, if we're lucky, only once per century. Somewhere in the cosmic filing cabinet of human discovery, a drawer was left open, a label was misplaced, and the consequence was a correction so profound it shifted our understanding of the solar system's outer limits. This was no typo, no rounding error in a spreadsheet. This was a misidentification so fundamental it cut to the core of how we order the universe. It revealed a chilling truth. Sometimes the most terrifying monsters are not the ones lurking unseen in the darkness, but the ones we have already photographed, measured, and filed away under the wrong name, believing them to be docile. The year was 2014. The cameras pointed at the Chilean skies weren't searching for icy wanderers. Their mission was far more esoteric: to map the invisible architecture of reality itself. The Dark Energy Survey was a monumental project designed to trace the clustering of galaxies, to measure the accelerated expansion of the cosmos, to document the slow, grand warping of space-time across billions of years. But every night, as those sophisticated lenses stared into the profound void, they also captured something much closer to home. Something that, in the grand cosmological scheme, shouldn't have mattered. A speck. A dot. A trivial piece of local data drifting through the starfields. At the time, no one understood this speck was a threat hiding in plain sight. It appeared across multiple archived images, a single, unblinking point of light inching with glacial patience against the fixed backdrop of the galaxy, like a ghost passing silently through walls. Astronomers have a term for these post-facto revelations: archival detections, and they carry a peculiar, insidious danger. When you find something in real time, alarms sound, telescopes swivel, the global network of observers scrambles. But when you uncover something years after the light has already hit the sensor, there is no urgency, no immediate follow-up, just a dim, cold speck in old data sitting patiently in a database, waiting for its moment to be understood. This is the precise, quiet drama that unfolded with catalogue designation C2014-UN271, later named Bernardinelli-Bernstein. At roughly 30 astronomical units from the Sun, out near the orbit of Neptune, this object should have been screaming its identity. If it were a comet, it should have been glowing, outgassing, trailing the faintest haze of sublimating ices. But it wasn't. It appeared clean, solid, planet-like. That absence of fuzziness, that lack of what astronomers call a coma, made it look exactly like what it was not: a benign dwarf planet, a frozen citizen of the outer solar system drifting through the Kuiper belt or the scattered disk, minding its own business. To appreciate the trap, you must understand the detection logic. When you see a bright object at 30 AU, You work backwards. You measure its brightness. You make an assumption about its reflectivity, its albedo, and you solve for its size. The logic is sound. Dwarf planets are typically dark, rocky or icy worlds that reflect little sunlight. Comets, by contrast, are often small but appear bright because they're wreathed in clouds of gas and dust that scatter light in all directions. Bernardinelli-Bernstein was bright, but it had no cloud. Therefore, the inescapable conclusion from the math was that this thing had to be enormous. The numbers that came back were not just surprising. They were, in a quiet academic sense, terrifying. Initial calculations suggested a width of 120 to 137 kilometers. This was larger than any comet nucleus ever observed. Larger than many moons. A frozen behemoth had been lurking in the archives, and no one had panicked because it was filed under the wrong name. It perfectly fit the profile of a distant icy planetoid. Its orbital arc made sense for such an object. Its brightness made sense. Everything was consistent, neat, and orderly. Everything except the one thing that mattered most, what it actually was. Scientific papers have a way of burying cataclysmic revelations under layers of cautious, bloodless language. Phrases like notably large and exceptional diameter sound calm, professional, measured. They are the lexicon of dispassionate observation. But translate those phrases into plain English, and what they really mean is this. We found something that breaks our scale. We found something that does not fit. We found a category error drifting through space, and we almost missed it entirely because our system told us it was something else. This leads to the question that should coil in your mind like cold smoke. If the largest comet ever discovered spent years masquerading as a minor planet, how many other objects are sitting in our databases, similarly misfiled? How many slow-moving giants are adrift in the outer darkness right now, catalogued as harmless debris, waiting for a curious graduate student or a smarter algorithm to realize they are not harmless at all? The mistake with Bernardinelli-Bernstein was only corrected because someone decided to look closer, to question the label. But there is no law of the universe that guarantees that will happen again. The next misidentified object might not grant us years of warning. It might give us months, or less. The truly frightening part isn't that astronomers made a mistake. The frightening part is that the mistake was perfectly logical. The reasoning was sound. The assumptions were reasonable based on everything we thought we knew. And that means we're not just dealing with simple human error. We're confronting a systematic blind spot in our cosmic vision, a flaw woven into the very framework we use to decide what is dangerous and what is not. Bernardinelli-Bernstein did not hide. It was right there, glowing faintly in the archived images, a siren ignored because we were listening for the wrong song. We saw it. We just didn't know what we were looking at. Let's talk about brightness, because brightness is the mask, the costume, the source of the entire illusion. When you stand under a clear night sky, every star is a perfect, dimensionless pinprick. Some blaze with fierce intensity, others are faint, delicate smudges at the edge of vision. Your brain, honed by evolution on a world of close horizons, instinctively equates that brilliance with size or proximity. The bright ones must be bigger or nearer. In astronomy, however, brightness is a liar, a trickster. It reveals almost nothing about the true nature of what you're seeing without a dictionary of context. A pebble tumbling close to Earth can burn with the same apparent fire as a mountain drifting beyond Saturn. A surface as dark as charcoal can cloak a continent-sized mass. And when you're analysing an object 30 astronomical units from the Sun, a staggering 2.8 billion miles away in the frigid, sun-starved void, brightness transforms from a simple fact into a puzzle with a multitude of possible equally valid solutions. Bernardinelli-Bernstein was bright, not dazzling, not a beacon screaming for attention, but measurably, persistently bright for something so profoundly distant from the sun's warming embrace. And that persistent brightness created a deceptively simple problem for astronomers. They had to solve the cosmic equation backwards. How large must an object be to shine with this particular intensity from this specific, unimaginable distance? The answer hinges entirely on a single critical variable: albedo. A fancy term for a simple concept: reflectivity. How much of the sun's faint, distant light does the surface bounce back into the blackness of space? A pristine ball of ice acts like a celestial mirror, throwing most of the light back. A lump of cosmic charcoal, a dark porous rubble pile, absorbs it. That difference changes everything. Typical comet nuclei, the solid frozen cores buried beneath the glorious streaming coma and tails, are modest things. They are dirty snowballs, ranging from perhaps 1 to 10 kilometers across. They are dark, porous, and grim, with albedos hovering around a mere 4 to 6%. This means they swallow 94 to 96% of the sunlight that falls upon them. They are among the blackest objects in the solar system. But Bernardinelli-Bernstein, in its initial silent guise, wasn't behaving like a typical comet. It showed no halo, no tail, no visible sign of gaseous release. Faced with this clean, point-like appearance, astronomers made the logical, reasonable assumption: it must have a higher albedo. Perhaps it was more like some icy denizens of the Kuiper belt, with surfaces that reflected 10, maybe even 15% of the light. That assumption, plugged into the equations, yielded the first round of size estimates. A sphere roughly 100 kilometers in diameter. The number was staggering. It was unprecedented in the context of comets, but it still felt just barely within the realm of icy bodies we believed we understood. A record breaker, yes, but not a category destroyer. Then the refinements began. This is how science operates at its best. A slow, meticulous chipping away at uncertainty. More observations trickled in from other telescopes. Orbital calculations grew more precise, tracing its long arc backward into time. Spectroscopic data began to offer faint hints about surface composition, and with each new data point, the estimated albedo began to drop. This is the crucial pivot. In the math of distant detection, albedo and size exist in a tense inverse relationship. If an object is darker than you initially thought, it must be physically larger to account for the same observed brightness. It is the cosmic equivalent of realizing a faint, distant campfire you spotted is not a small, bright blaze, but a massive, smouldering bonfire made of wet, dark wood. As the albedo estimates for Bernardinelli-Bernstein were revised downward, the size estimates had nowhere to go but up. The final numbers settled into a range that sounded, to many, almost absurd: 120 to 137 kilometers in diameter. To grasp that scale, consider a drive from Los Angeles to San Diego. This comet's nucleus is wider than that journey. It is not a mountain in space. It is a floating mountain range, a silent, frozen territory. A world that was, for a time, successfully pretending to be merely a large comet. This is where the Kuiper belt logic trap springs shut. The Kuiper belt, that donut of icy debris beyond Neptune, is full of large objects. Pluto is there, Eris, Makemake, Haumea. These are proper worlds, with diameters measured in the hundreds or thousands of kilometers, so finding something even 130 kilometers wide out in that general neighborhood shouldn't, in theory, be shocking. It should be par for the course. Except Bernardinelli-Bernstein wasn't sitting quietly in the Kuiper belt. It was falling. Its orbit was not a near-circular track in the planetary suburbs. It was a monstrous ellipse, a long, skinny arc of such extreme proportions it whispered of a far more distant and mysterious homeland. It was coming from somewhere far beyond the known Kuiper belt, from a region we can barely comprehend and cannot directly observe, the Oort cloud. And this changed the entire statistical story. The Kuiper belt, while vast, is close enough that we have surveyed it fairly well. We understand its population distribution. We have models that predict how many objects of a certain size should exist, and roughly where. But the Oort cloud? That is a different reality altogether. It is a hypothetical sphere, a vast, thick shell of icy debris believed to surround our solar system, at distances ranging from 2,000 to 100,000 astronomical units. It remains almost entirely theoretical, a ghost inferred from the trajectories of the comets that occasionally fall inward from random directions. And those comets, the long-period comets we have seen for millennia, are almost universally small, a few kilometers across, maybe 10 on the extreme end. The very idea that the Oort cloud could harbour and then hurl inward an object 130 kilometers wide was not just surprising, it wasn't part of the model. It was an anomaly that broke the population curve. Scientists began running the numbers in a new, uneasy context. How many objects of this size could the Oort cloud contain without us having seen one before? How statistically rare is Bernardinelli-Bernstein? Is it a 1 in a billion fluke, a cosmic lottery winner that we, by sheer luck spotted in our brief sliver of geological time? Or is it the first detected member of an entire population we never knew existed, the giants of the Oort cloud? The math did not provide comforting answers. If Bernardinelli-Bernstein is truly unique, then our luck is almost unnervingly good. We witnessed a singular event. But if it is not unique, if it is merely the first of dozens or hundreds of similar-sized objects drifting in that infinite dark, then we have been living under a cosmic sword of Damocles without ever sensing the thread growing thin. The moment this realization crystallized was the moment the entire narrative shifted. This was no longer just a very large comet. This was an anomaly, a category breaker, an object that forced astronomers to rip a page out of their textbooks on solar system formation and mass budgets. It demanded they rewrite their deepest assumptions about what the frozen darkness beyond Neptune truly contains, and how much forgotten, frozen mass might be lurking there, waiting. And the terrifying part, the sheer size alone doesn't even explain what happened next. Because Bernardinelli-Bernstein wasn't done revealing its secrets. It was, in the most chillingly literal sense, just starting to wake up. For a period of time that felt both brief and eternal in the slow-motion world of astronomical discovery, see 2014 UN 271, Bernardinelli-Bernstein, sat in the catalogues as a dwarf planet candidate. It was a fascinating, record-breaking trans-Neptunian object, a curious icy world to be tracked and studied, but it minded its own business. Astronomers refined its immense orbit with greater precision, calculating with awe its aphelion in the deep Oort cloud and its future path inward. They traced its provenance and plotted its destiny, and then, in a series of observations taken when the object was between 16 and 20 astronomical units from the Sun, still far beyond Uranus, something impossible, something quietly revolutionary happened. The silent point of light began to breathe, outgassing. The term sounds clinical, technical. In reality, it is one of the most fundamental and elegant processes in the solar system. Imagine a frozen lake in the deepest part of winter. The water is locked in stasis, a solid plane held captive by cold, but when spring arrives and the sun's angle changes, warming the surface, the ice doesn't just melt in placid sheets. At the molecular level, a more direct transformation occurs. Some of the ice skips the liquid phase entirely, its molecules vibrating with newfound energy until they break free directly into vapor. This is sublimation. In the vacuum of space, where pressure is effectively zero, sublimation is the dominant rule. Water ice, methane ice, carbon dioxide ice, they all sit in frozen silence on the surfaces of distant worlds until the faint distant whisper of sunlight provides just enough energy to turn them into gas. And when that gas escapes, it creates jets, it forms plumes. It is the signature of activity, the definitive proof that a comet is stirring from its billion-year slumber. The key player in this awakening was carbon monoxide. Astronomers call ices like this supervolatiles. They don't need much heat to sublimate. Water ice requires temperatures above about 200 Kelvin to start outgassing in significant amounts. But carbon monoxide, it begins its transformation from solid to gas at temperatures well below 150 Kelvin. That is profoundly cold. That is the bitter, sunless cold of the space around Neptune, and that is precisely where Bernardinelli-Bernstein started showing the first faint signs of life. The instrument that made this invisible breath visible was the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. ALMA is not a single telescope but a symphony of them, a collection of ultra-sensitive radio dishes designed to detect the faintest whispers of cold gas in the universe. When astronomers pointed ALMA's collective ear toward Bernardinelli-Bernstein, they weren't sure what, if anything, they would hear. The object was still so far from the Sun, so deeply frozen, that conventional wisdom suggested it should be inert. What came back through the data was unmistakable, the spectral signature of carbon monoxide. Not a faint uniform whisper, but a clear signal. And more importantly, the data suggested this gas wasn't leaking evenly from the entire surface in a gentle, diffuse haze. It was streaming off in localized jets, concentrated in specific regions, as if pressurized vents had cracked open on the frozen crust. This wasn't a slow seep. It was a focused exhalation, the kind that happens when subsurface ice, warmed by the faintest trickle of solar energy, begins to sublimate in a confined space. The gas builds pressure beneath the surface until it finds a weakness, a crack, a pore, a fissure from an ancient impact, and bursts through in a discrete jet. Here is what notably didn't happen. Bernardinelli-Bernstein did not suddenly sprout a magnificent glowing tail visible to amateur telescopes. It did not transform into the classic romantic image of a comet, with a banner of gas and dust streaming millions of miles behind it. At 16 to 20 AU, it was still far too distant, far too cold for that kind of dramatic, dusty display. What it did instead was reveal its true nature in a subtle, spectroscopic whisper. Those jets of carbon monoxide were the smoking gun. This was no dwarf planet. This was unequivocally a comet, but a comet unlike any ever witnessed before. The continued absence of a visible coma suddenly made brilliant sense when viewed through the lens of gravity. A coma, that fuzzy cloud around a comet's nucleus, forms when outgassing becomes intense enough that the escaping gas and dust create a persistent sun-scattering atmosphere around the core. But Bernardinelli-Bernstein is so massive that its own gravity, tiny by planetary standards but formidable for a comet, exerts a significant pull. Some of that escaping carbon monoxide gas doesn't just fly freely into space, it is tugged back, held close, unable to fully escape the object's gravitational grasp. The outgassing is real, measurable and active, but it is not yet powerful enough to overcome the object's own field and create the classic, fuzzy coma. It is like watching a geyser emit steady plumes of steam against a grey sky, without the dramatic eruption column. The activity is undeniable, but you have to know where and in what wavelength to look. Why does this distinction matter so profoundly? Because those faint cold jets revealed something fundamental about Bernardinelli-Bernstein's history and composition. Comets that have made multiple punishing journeys through the inner solar system are like old soldiers, battered and changed. Their surfaces develop thick, insulating crusts. The most volatile ices near the surface sublimate away on each pass, leaving behind a lag deposit of dust and non-volatile rubble, a black crusty shell that shields the pristine interior from further erosion. But Bernardinelli-Bernstein is pristine. It is a virgin. It has never been this close to the Sun before in the 4.16 billion-year history of the solar system. Its surface still contains these super-volatile ices, like carbon monoxide, preserved in a deep freeze from the air of the solar nebula itself. This object is a time capsule, a frozen archive of the primordial cloud from which our planets formed, and it is now falling inward for the very first time in recorded history. And here is the part that should make the hair on your arm stand up. This thing has barely begun to wake up. It is still cruising along beyond the orbit of Uranus. It will not reach its perihelion, its closest, warmest approach to the Sun, until January of 2031. And even at that point of maximum intimacy, it will only come as close as 10.9 astronomical units, which is still just inside the orbit of Saturn. That remains incredibly, almost disappointingly far. But it is close enough that the solar heating will intensify, the jets will strengthen, the physics of sublimation will shift into a higher gear, and if subsurface ice has been building pressure in sealed pockets for millions of years, with no previous release, there is no reliable model, no historical precedent to tell us what will happen when the Sun's warmth finally penetrates deep enough to trigger a full-scale eruption. We are not watching an old, tired comet fade. We are witnessing a primordial giant wake up for the very first time, and we have a front-row seat to a process that has never been observed at this scale. Humans are spectacularly, hilariously ill-equipped to comprehend cosmic scale. Our brains evolved to navigate a world of trees, rivers, and horizons. A mountain is big, an ocean is vast. But when the numbers ascend into the hundreds of kilometers for size and billions of miles for distance, our mental machinery short-circuits. The figures become abstract, devoid of meaning. It's too big, too far, too alien. So let's try to bridge that gap with a comparison that might actually anchor this Leviathan in your mind. Right now, the astronomical community is often abuzz about various comets entering the inner solar system. Let's take a hypothetical, notable one. Say, a comet roughly 10 kilometers in diameter. To put that in human terms, picture Mount Everest. That towering summit, 8.8 kilometers above sea level, embodying the very concept of a colossal mountain. A 10-kilometer comet is essentially a Mount Everest tumbling through the void. If you could stand on its surface, You would feel the curvature, you would see a horizon, it would feel like a world. A small, rugged world, but a world nonetheless. Now take that mountain, that 10-kilometre comet, and multiply its width by 13, not its mass, its diameter, because Bernardinelli-Bernstein is approximately 130 kilometres across. For a geographic anchor, consider the state of Florida. From its Atlantic coast to its Gulf Coast panhandle, the peninsula stretches about 200 kilometres at its widest point. Bernardinelli-Bernstein is 2/3 the width of Florida. It is no longer a mountain. The scale has shifted. It is a landscape, a frozen county, a substantial piece of real estate adrift in the absolute black. It is massive enough that if you stood on one side, the opposite horizon would be dozens of kilometres away, lost in the gentle curve of its own icy surface. But here is where the simple analogy fails, and the mathematics become truly disturbing. Mass does not scale linearly with diameter, it scales with volume, and volume grows with the cube of the radius. If you double the diameter of a sphere, you increase its volume, and thus its mass, assuming similar density, by a factor of 8. So when you go from a 10-kilometre comet to a 130-kilometre comet, you're not dealing with something merely 13 times more massive. You're dealing with an exponential leap. Current estimates, heavily dependent on assumptions about its density, is it a fluffy rubble pile or a more consolidated icy world, suggest Bernardinelli-Bernstein could be over 1,000 times more massive than our hypothetical 10-kilometre comet. Not 13 times, 1,000 times. That is the difference between a grand cathedral and the mountain it's built upon, between a boulder and the entire mountain range that spawned it. This leads us to the critical concept of thermal inertia, the property that makes large objects behave in a fundamentally different way than small ones. Drop an ice cube on a hot sidewalk. It melts, then vanishes in moments. The heat penetrates its tiny mass almost instantly. Now, place a glacier under the summer sun. It persists for months, years, centuries. Its immense volume acts as a thermal buffer, resisting change, responding with glacial slowness. The phrase is literal. Bernardinelli-Bernstein is not an ice cube. It is a glacier. It is a frozen world so massive that the sun's warmth, even at its future closest approach, can only penetrate a few meters, perhaps a few tens of meters, into its surface. The interior, the overwhelming bulk of its being, remains forever untouched by stellar warmth, preserved at the temperature of deep space, potentially as cold as 20 or 30 Kelvin. This profound thermal inertia is why the unsettling informal term world eater has begun to circulate in discussions among astronomers. It's a metaphor borrowed from science fiction, but it captures an essential truth about scale. This isn't a comet in the traditional Rosetta mission sense. It is a rogue planetoid, a frozen moon that escaped the gravitational influence of the giant planets during the solar system's chaotic youth and was thrown into the Oort cloud, only to now be reeled back in by the sun's persistent grasp. And if it were on a collision course with Earth, which it absolutely definitively is not, its orbit is known with exquisite precision. The impact would be measured not in megatons or gigatons, but in exatons. It would be an extinction-level event so far beyond the Chicxulub impact that the latter would seem like a warning shot. It would not merely end an era of life, it would fundamentally reshape the geophysics of the planet, boiling oceans, cracking the crust, and blasting parts of the atmosphere into space. Before any panic takes root, let this be the bedrock. Bernardinelli-Bernstein poses zero impact risk to Earth. None. Its 2031 perihelion will place it a safe and sound 1 billion miles from our planet. The danger it represents is not one of trajectory but of category. Its very existence, falling inward from the Oort cloud, forces a deeply uncomfortable question upon us. What else is out there? How many other Bernardinelli-Bernsteins, these slow-moving, dark, city-sized glaciers of ice and rock, are currently drifting through the unimaginable distances of the outer solar system, too faint and too slow to trigger our automated survey alarms, waiting to be noticed only when they are already well on their inward journey? The danger is not this specific comet. The danger is the population it may represent. We have built our threat assessment models on the assumption that the truly colossal impactors are either extremely rare or are already in stable orbits we know about. Bernardinelli-Bernstein proves that a colossal object can come from a reservoir we cannot effectively survey, can be discovered only by chance in old data, and can be among us for years before we understand its true nature. That is the Florida-sized problem, not the object itself, but the gaping hole in our awareness its discovery revealed. For decades, the title of most dangerous object known to humanity has been held, undisputed, by a comet named Swift-Tuttle. Discovered in 1862 and rediscovered in 1992, Swift-Tuttle is a periodic comet with a nucleus estimated to be about 26 kilometers in diameter. It orbits the Sun every 133 years, and its path, when carefully calculated far into the future, occasionally brings it uncomfortably close to Earth's orbit. Not on a collision course in any foreseeable millennium, but close enough that astronomers have calculated a small, non-zero probability of an impact in the astronomically distant year of 40 Thor 79. The numbers surrounding a hypothetical Swift-Tuttle impact are the stuff of legitimate nightmares, an energy release equivalent to roughly 27 times the Chicxulub impact that ended the Cretaceous period. It is a civilization ender, a legitimate nightmare scenario that has rightly earned its fearsome reputation and cemented its status as the king of cosmic threats. But here is the profound problem with crowning Swift-Tuttle. Its danger derives almost entirely from its orbit, not its size. A 26-kilometer comet on a collision course is, without a doubt, globally catastrophic. It would be an event that resets the biosphere. But a 130-kilometer comet on a collision course exists in a different tier of catastrophe altogether. That is not an extinction event. That is a planetary reset button. That is the difference between wiping out most complex life on Earth and wiping out the very conditions that allow any life, perhaps even the planet's ability to hold a substantial atmosphere, to exist at all. Bernardinelli-Bernstein is nearly 5 times wider than Swift-Tuttle. To grasp the chasm between them, we must return to our geological touchstone, the Chicxulub impactor. The asteroid, or perhaps comet, that ended the age of the dinosaurs 66 million years ago is estimated to have been between 10 and 15 kilometers in diameter. That single impact released energy on the order of 10 billion Hiroshima bombs. It excavated a crater 180 kilometers wide. It ejected enough pulverized rock and sulfur into the upper atmosphere to shroud the planet in a global twilight for years, collapsing photosynthesis, shattering food chains, and erasing roughly 75% of all species. Bernardinelli-Bernstein is approximately 9 to 13 times wider than the Chicxulub impactor. Scaling up diameter by a factor of 10 increases volume, and thus mass, assuming similar density, by a factor of 1,000. Even accounting for comets being less dense than asteroids, Bernardinelli-Bernstein likely carries hundreds of times more mass than the dinosaur killer. An impact from such a body would not cause a mass extinction. It would cause a planetary sterilization event. The oceans would not just heat up, they would flash boil in places. The crust would not just fracture locally, it would undergo global seismic trauma. The atmosphere wouldn't just be polluted, it would be partially stripped away. We are discussing an event that would alter the geological and atmospheric identity of the Earth for eons. This stark comparison leads to a question that nobody in the institutional planetary defense community seems to be asking loudly enough. Why is our focus so intensely, perhaps myopically, trained on near-Earth objects when the real monsters, the true existential risks, appear to reside in the outer solar system? The entire architecture of planetary defense has logically prioritized fast-moving asteroids in Earth-crossing orbits. This makes sense on a spreadsheet. Those are the immediate frequent short warning time threats. They are the ones we can, in theory, practice on. But embedded in that focus is a deep-seated, rarely questioned assumption that truly large impactors, the planet killers, are incredibly rare, that we've already found most of the big ones in orbits that could concern us, and that anything large enough to be catastrophic will be detected with decades or centuries of advance warning, giving us time to mount a response. Bernardinelli-Bernstein proves every part of that assumption is flawed, or at least incomplete. This object was sitting in archival data for 7 years before its true identity was understood. It is enormous. It is not hiding in the asteroid belt. It is not lurking on some quirky near-Earth orbit. It came from the Oort cloud, a region so distant, so sparsely surveyed, that we have no statistical certainty about how many of its kin exist. Our size-based threat model has a blind spot, and that blind spot is shaped exactly like a slow-moving, dark, giant comet. So yes, Comet Swift-Tuttle retains its crown as the most dangerous object whose orbit we know well enough to worry about in the very long term. But Bernardinelli-Bernstein is dangerous for a far more insidious reason. It reveals that our entire survey system, our early warning network, is not designed to catch slow-moving giants until they are already well inside the planetary realm, already years into an inbound journey that began millions of years ago. By the time we spotted this one, it had been approaching since before the dawn of human civilization. We didn't discover it in real time, we stumbled across its ghost in old data, and then spent years deciphering what it was. That is not a detection system. That is an audit failure, a lucky find during a retrospective check. And if Bernardinelli-Bernstein is the newly discovered king of comets by sheer physical scale, then the throne room it implies is terrifying. How many other kings and queens are waiting in the outer darkness, drifting inward on similar long, slow arcs, currently uncatalogued, unnamed, and unseen? The king is not just the comet. The king is the unsettling truth it carries. Our sky is not as transparent, nor our vigilance as complete as we desperately need to believe. To understand the true significance of Bernardinelli-Bernstein, we must journey to the place of its origin. Because the Oort cloud is not merely distant, it remains, in practical terms, a hypothesis. We have never directly imaged it, never resolved a single one of its trillions of constituent objects. We infer its existence the way a detective infers a storm from leaves scuttling across a street. Comets arrive from seemingly random directions, tracing back on immense elliptical orbits that point to a vast spherical shell enveloping the solar system. The gravitational math leaves no alternative. Something out there, between 2,000 and 100,000 astronomical units from the Sun, must act as a reservoir, a gravitational deep freeze holding billions, perhaps trillions, of icy bodies in a tenuous grip. This is the Oort cloud, a spherical halo of frozen debris, the leftover building material from the solar system's formation, preserved in a state of near absolute zero for 4.6 billion years. The traditional model of the Oort cloud is one of small shattered remnants. It should contain, the theory went, mostly objects a few kilometers across, maybe 10 at the extreme. These were the icy pebbles and boulders ejected during the solar system's violent adolescence, when the migrating giant planets, particularly Jupiter and Saturn, acted like gravitational titans, flinging protoplanetary debris in every direction. Most were ejected entirely into interstellar space. A fraction were thrown just hard enough to reach Ophelia in this distant halo, where the sun's gravity is a whisper but still a bond. The idea that this cloud could harbour and then deliver an object 130 kilometres wide was not just unexpected, it was antithetical to the model. Objects of that size should have either successfully accreted into a planetary core closer to the Sun, or been completely ejected by gravitational encounters during the chaos. They should not be sitting quietly in the deep freeze, pristine and intact, waiting to fall back inward like a forgotten weapon. But Bernardinelli-Bernstein exists. Its existence forces a monumental revision. The mass budget for the Oort cloud is wrong. If there is one object this size, there are almost certainly more. And if there are more, then the total mass of the Oort cloud is significantly higher than anyone calculated. This has profound implications. It means the early solar system was even more violent and dynamic than our best simulations suggest. It means planetary migration through far more material and far larger pieces of material outward than we thought. The Oort cloud is not just a graveyard for comet-sized debris. It is a holding tank for failed planetary building blocks, for frozen, unfinished worlds that never got the chance to grow up. How did something as large as Bernardinelli-Bernstein end up so impossibly far from the Sun? The most plausible explanation is a story of ancient violence. 4.5 billion years ago, the solar system was a shooting gallery. The giant planets were not in their current stately orbits. They were migrating, jostling for position, amidst a thick disk of planetesimals. Their gravitational interactions were brutal. Objects were flung inward, fueling the late heavy bombardment. Objects were ejected into the blackness of interstellar space, and a select few received a precise glancing blow, a gravitational kick that sent them on an immense journey. They were thrown not with enough force to escape forever, but with just the right impulse to reach the distant realm of the Oort cloud. their orbits so long they would not return for billions of years. Planetary migration models suggest Neptune ploughed outward through a dense belt of icy bodies, scattering them like cosmic billiard balls. Bernardinelli-Bernstein likely formed in the region between the orbits of Uranus and Neptune, growing to its tremendous size before a close encounter with an ice giant gave it the gravitational slingshot that exiled it to the outer darkness. But there is another, more speculative and enthralling possibility. What if Bernardinelli-Bernstein is not native to our solar system at all? What if it was captured? Stars are not born in isolation. They form in clusters, in stellar nurseries where hundreds of sibling suns are packed relatively close together for millions of years. During this early crowded period, close flybys between stars are common. Another star could have passed within a few thousand astronomical units of our infant sun, close enough for their gravitational spheres of influence to briefly mingle. In such an encounter, loosely bound objects in the outer reaches of one system can be stripped away or donated. What if Bernardinelli-Bernstein formed around another star, and during a primordial stellar close encounter, it was gravitationally plucked from its birthplace and adopted by our Sun? This would elegantly explain its size. It wouldn't have been subject to the collisional grinding that likely pulverized most of our native Oort cloud objects. It would have arrived fully formed, a frozen world from a foreign solar system, a cosmic immigrant captured in our Sun's embrace. We would never know for certain unless we could sample its material and find isotopic ratios that don't match the rest of our solar system, a task currently far beyond our reach. None of this is proven. It is plausible, consistent with the physics, and deeply fascinating. But it underscores the frustrating, exhilarating truth Bernardinelli-Bernstein has unveiled. It raises far more questions than it answers. Where did it truly come from? How many of its siblings are still out there? Is it a fluke, a statistical outlier we were bizarrely lucky to catch? Or is it the first specimen of a dominant yet hidden population of Oort cloud giants? The only way to answer these questions is to look harder, to survey the outer darkness with more sensitive eyes, to reinterpret our archives with smarter tools. Because if there is one Bernardinelli-Bernstein, there might be 10. And if there are 10, we desperately need to know where they are and where they are going. The cloud that shouldn't exist does, and within it may drift more frozen kingdoms than we ever dared imagine. Here is a question that sounds simple but unravels into philosophical chaos the moment you pull at its threads. What, fundamentally, is a comet? The textbook answer is straightforward. A comet is a relatively small, icy body that, when heated by the sun, releases gas and dust, forming a visible coma and often a tail. Asteroids are rocky or metallic and do not outgas. Planets are large enough to have cleared their orbital neighbourhood and achieved hydrostatic equilibrium, a spherical shape from their own gravity. Clean, neat, tidy. Except when you apply these definitions to the messy reality of the solar system, the categories immediately collapse. Consider Pluto. For 76 years, it was the 9th planet. Then, in 2006, the International Astronomical Union refined the definition of a planet, requiring it to have cleared the neighbourhood around its orbit. Pluto, which shares its orbital space with thousands of other Kuiper Belt objects, was demoted to dwarf planet. By that strict definition, however, Neptune hasn't cleared Pluto from its path, so the taxonomy frays at the edges. The point is this: classification systems are human constructs. They are tools for organising information, for making sense of complexity. But the universe operates on a continuum of physics. It does not care about our filing cabinets, and Bernardinelli-Bernstein is proving this point in the most spectacular way possible. So, what is it? Is it a comet? It outgasses. It has jets of carbon monoxide streaming from its surface. Its orbit originates in the Oort cloud, the reservoir of long-period comets. By the traditional functional definition, yes, it is a comet. But it is also 130 kilometers wide, which places it firmly in the size range of small dwarf planets like Ceres or Enceladus. Its behaviour is hybrid. Its gravity is strong enough to influence its own outgassing, holding back a coma. Its thermal inertia is that of a planetary body, not a small icy dirt ball. If you could strip away its volatile shell, you would likely find a differentiated interior, a rocky core, layers of high-pressure ice, more akin to a moon than to the porous, homogeneous rubble pile of a typical comet nucleus. So perhaps Bernardinelli-Bernstein is a transitional object, a missing link that sits squarely on the boundary between comet and dwarf planet. belonging fully to neither category. Astronomers have a name for icy bodies that orbit between Jupiter and Neptune and exhibit comet-like activity: centaurs. Bernardinelli-Bernstein began its current inbound journey as a centaur-like object billions of years ago before its orbit evolved, but calling it a centaur just kicks the can down the road. It names the orbit, not the essence. Here is a more provocative idea. What if Bernardinelli-Bernstein is a failed planet core? During the solar system's formation, planetary embryos collided and merged to form the worlds we know. But not every embryo succeeded. Some were scattered by gravitational chaos before they could finish accreting. Some were ejected entirely, and some perhaps were thrown just far enough to the Oort cloud, frozen in time, never completing their journey to planethood. Bernardinelli-Bernstein might be one of these orphaned cores, a fossilized relic of a planet that never was, now returning from its billion-year exile. If that's true, then the distinction between comet and planet becomes not just murky, but almost meaningless. The only difference between Bernardinelli-Bernstein and the dwarf planet Ceres might be that the former retained a thick primordial mantle of supervolatile ices, while Ceres lost most of its volatiles eons ago. Structurally, they could be near identical twins, yet we label one a dwarf planet and the other a comet based almost entirely on where we found it and whether we saw it fuzz up. Our taxonomy crumbles under the weight of this single object. Why does this semantic struggle matter? Because how we classify an object directly influences how we study it and, critically, how we assess the risk it represents. If Bernardinelli-Bernstein is filed under Comet, research focuses on outgassing dynamics, dust production, and coma chemistry. If it is classified as a planetary body or dwarf planet, the focus shifts to internal structure, geology, differentiation, and long-term thermal evolution. For planetary defense, the classification is not academic, it is strategic. It determines which survey programs get funding, which observational techniques are prioritized, and which objects are flagged for follow-up. If we assume large, hazardous objects are only asteroids in near-Earth orbits, we design our searches to find fast-moving, rocky dots. We might intentionally filter out slow-moving, point-like objects in the outer system, dismissing them as harmless dwarf planets. Bernardinelli-Bernstein is the perfect trap. It looks like the latter, but has the potential destructive capacity of 1,000 of the former. This lesson extends beyond our solar system to the study of exoplanets. As we've discovered thousands of worlds around other stars, we've found that the categories we invented for our own cosmic backyard are provincial and inadequate. Hot Jupiters should not exist so close to their stars, but they do. Super-Earths have no analogue here, but they are common elsewhere. The universe produces every conceivable variation on the theme of matter orbiting stars. Our job is not to force these creations into our neat earthbound boxes. Our job is to describe what they are, to understand their physics, even if that means admitting our definitions were always provisional, always incomplete. Bernardinelli-Bernstein is teaching us that lesson the hard way, in our own celestial neighbourhood. It is not a comet, it is not a dwarf planet, it is something in between, something for which we lack a perfect name, and that is perfectly okay. The universe is under no obligation to make sense to our filing systems. The terror it evokes isn't just from its size, but from its refusal to be categorized, a reminder that nature's inventory is far stranger and more diverse than our catalogues can hold. There is something deeply unnerving about watching a monster wake up in slow motion. Bernardinelli-Bernstein is not exploding. It is not violently fragmenting. It is, for now, simply breathing, exhaling faint jets of carbon monoxide in the perpetual night 16 to 20 astronomical units from the Sun, a distance where the textbook said comets should still be in hibernation. This quiet activity is more unsettling than a sudden flare because it is a prelude without a known finale. We don't know when the real show begins. We don't know at what precise distance subsurface pressure will overcome the tensile strength of its crust. We don't know if there are vast sealed chambers of volatile ice beneath its surface, like cosmic champagne bottles under pressure for millions of years, waiting for the cork to pop. We are watching the opening credits of a film that will take a decade to fully unfold, and we have no spoilers, no script. We are flying blind into the climax of a story written by gravity and thermodynamics. The key to understanding this delayed reaction is thermal lag. Imagine searing a thick steak. The surface sizzles and chars immediately, but the centre remains cool, slowly warming over minutes. Heat does not teleport, it diffuses, molecule by reluctant molecule. The thicker the material, the longer the delay. Bernardinelli-Bernstein has been falling sunward for millions of years, but only in the last few thousand has it entered a region where solar radiation has any meaningful warming effect, and that feeble heat is still in the process of inching its way downward, centimetre by century, sublimating the most volatile ices first, creating microscopic pockets of gas that build pressure in the darkness. This thermal inertia is what separates a celestial glacier from a celestial snowball. Here is what keeps planetary scientists staring at ceiling tiles at 3 a.m. We have no idea how stable the crust of this thing truly is. Comets fragment routinely. Shoemaker-Levy 9 broke into more than 20 pieces before its fiery rendezvous with Jupiter. Comet Ison disintegrated during its solar close encounter. But those were small comets, a few kilometres across, with negligible gravity and fragile, porous structures. Bernardinelli-Bernstein is different. Its own gravity is a significant force, a binding energy that holds it together against all but the most extreme stresses. But pressure is a relentless adversary. If subsurface gases build to critical levels, if there are ancient fault lines from forgotten impacts, if thermal expansion creates cracks that propagate deep, then even this behemoth could succumb to fracture. Fragmentation wouldn't mean a Hollywood-style explosion. It would be more geological, a carving event. A chunk several kilometres across, itself a sizable comet, could shear off from the main nucleus, like an iceberg from a glacier. This new fragment, with fresh volatile-rich surfaces suddenly exposed to the vacuum, would begin outgassing furiously, potentially sprouting its own brilliant coma and tail. It would become a spectacular secondary event, and it would also introduce chaos into our calculations, because the non-gravitational forces from that new jetting would alter the orbits of both pieces in unpredictable ways, making long-term trajectory forecasts far more difficult. But there is a scenario rarely discussed in official papers because it sounds like the domain of science fiction, yet it is physically possible. What if it doesn't fragment at all? What if Bernardinelli-Bernstein holds together, intact, all the way to its 2031 perihelion at 10.9 AU, and the outgassing simply intensifies to a level we have never before witnessed? What if those jets become geysers, lifting not just gas but plumes of dust and ice crystals high above its surface, creating a coma hundreds of thousands of kilometres wide? What if the solar wind sculpts that material into a faint gossamer tail visible across the inner solar system? A comet the size of a small American state, glowing with a soft, eerie light near Saturn, a permanent fixture in the telescopic sky for years, a constant silent reminder of the scale and activity of the cosmos. That is not a prediction. It is a legitimate possibility within the laws of physics. The truth is, we have no reliable model for what a 130-kilometre comet does when it is heated. Every comet we've studied in detail has been small enough that its own gravity was an afterthought. Their outgassing is a surface phenomenon. With Bernardinelli-Bernstein, gravity is a key player, trapping its own atmosphere. Its internal structure, potentially layered, with insulating barriers and pressure traps, matters immensely. Its thermal history, a billion years in deep freeze, matters. We are making educated guesses, but we are in uncharted territory. And then there's the quiet, back-of-the-mind fear. What about a delayed eruption? What if, after perihelion, as Bernardinelli-Bernstein begins its long journey back to the outer dark, the accumulated heat from its close approach finally reaches a buried volatile deposit? What if, in 2035 or 2040, this object suddenly brightens by a factor of 100? Not because it's closer, but because something inside has finally given way. It would be a breathtaking astronomical event. And it would be the ultimate lesson in humility, demonstrating that comets are not static fossils. They are dynamic, chemically complex, pressurized systems. And when you scale that system up to planetary dimensions, the potential for surprise scales with it. We are on a silent countdown to an unknown event, and the clock set by orbital mechanics is utterly indifferent to our curiosity or our fear. Let's address the elephant in the room, or rather the Florida-sized elephant that drifted unnoticed through our cosmic backyard for 7 years. Bernardinelli-Bernstein was not discovered by a dedicated planetary defense telescope sounding alarms. It was found by accident during a forensic sift through archival data from the Dark Energy Survey, a project whose mission had nothing to do with the solar system. It was a happy accident, a testament to human curiosity. But in the context of protecting our civilization, it is not a success story. It is a glaring systems failure. It reveals a critical gap in our planetary immune system. Here's how modern survey astronomy typically works. Robotic telescopes scan the sky night after night. Software compares the images looking for movers, points of light that shift against the fixed background of stars. These are flagged as potential asteroids or comets. The fast-moving ones near Earth get immediate follow-up. The system is a pipeline, and it is brilliantly optimized for one thing: catching fast-moving, close-in rocks that cross Earth's orbit. It is not designed for, and is in fact poorly suited to, catching slow-moving giants from the outer solar system. The assumption has always been that slow movement equals great distance, and great distance equals no imminent threat. Bernardinelli-Bernstein shattered that assumption. It was moving slowly because it was far away, yes, but it was on a decisive inbound trajectory from a reservoir of unknown threats. The survey software flagged it, but as a low-priority curiosity. It didn't cross Earth's path, it showed no activity, it looked boring. So it was catalogued and largely forgotten, a line in a database, until someone looked closer and saw the monster hiding in the numbers. The forthcoming Vera C. Rubin Observatory promises to revolutionize this field. Previously known as the Large Synoptic Survey Telescope, it is designed to scan the entire visible sky every few nights with unprecedented depth, generating an avalanche of data. Its goal is to detect everything that moves, from city-killer asteroids to distant icy bodies, far faster than ever before. It is an essential, magnificent tool, but it is not a magic bullet. Even with Rubin online, a fundamental gap will remain. Detection is not characterization. Finding a new dot is the first step. You then need multiple observations over weeks or months to pin down its orbit. You need spectroscopy to learn its composition. You need time to understand it. If the object is beyond 20 AU, these tasks become exponentially harder. The light is desperately faint. Gathering enough photons for analysis takes precious time. Bernardinelli-Bernstein's orbit is now known precisely because we had those archival years to work with. But imagine if we had discovered it only last year, already at 15 AU with less than a decade to perihelion, with an orbit still highly uncertain. Would we know if it was a threat? No. We'd be in a race against time to gather enough data before it got even closer, all while the public and media demanded answers. This is the late discovery problem. Finding a hazardous object eventually is not good enough. We need to find it early, when it is still far enough away that a tiny nudge could turn a hit into a miss. Warning time is the most critical resource in planetary defense, more important than the size of the impactor. A 1-kilometer asteroid detected 20 years out is a manageable problem. A 100-meter asteroid detected 6 months out is a catastrophe. Our current systems are biased toward the latter scenario for near-Earth objects and are virtually blind to the former scenario for outer solar system objects. That is the surveillance gap, and Bernardinelli-Bernstein sailed right through it. Funding priorities cement this gap. Political and institutional support for planetary defense focuses on near-Earth objects because the risk feels tangible and imminent. No congressperson funds a telescope to look for comets that won't arrive for 10,000 years, but imminent risk is not the same as total risk. The total risk includes low probability, high consequence events, precisely the kind an Oort cloud giant represents. If we are serious about planetary defense, we must be brutally honest about our capabilities. We cannot deflect a 130-kilometer object. We likely couldn't even meaningfully perturb one with decades of warning using all our nuclear arsenals, and we certainly can't track them reliably yet. If there is a population of Bernardinelli-Bernsteins drifting inward, our current sense of security is a comforting illusion, built on a foundation of incomplete data. The gap is not just in the sky, it is in our risk assessment, in our budget allocations, and in our collective imagination. We have built a fence around our yard, but we haven't considered the giants that can step over it from a mile away. So, what is the final unifying thesis? What is the real takeaway from the saga of Bernardinelli-Bernstein? It is not merely a record-breaking curiosity. It is a warning label etched across the cosmos. A reminder that the universe operates on scales and timelines that humble our perceptions, and that our understanding of our own celestial neighbourhood remains stubbornly, dangerously incomplete. We thought we had comets figured out. We thought we knew their size limits, their origins, their behaviour. Then a point of light in an archive forced a rewrite. This forces a crucial distinction: expectations versus predictions. Expectations are what our models and biases tell us should be. Predictions are what the data, cold and hard, tell us will be. Our expectations said Oort cloud objects are small and dark. The data from Bernardinelli-Bernstein predicted, and then confirmed, a 130-kilometre nucleus venting gas at Neptune's distance. The expectation was wrong. The prediction, rooted in observation, was right. The lesson is to trust the data, especially when it contradicts the model. Order, we must accept, is an illusion we impose. We crave categories: comet, asteroid, planet. But the universe is a continuum. It produces every hybrid, every transitional form. Bernardinelli-Bernstein is both a comet and a dwarf planet, exposing our taxonomy as a convenient fiction. The categories are useful tools, but they are not reality. Reality is a spectrum of frozen worlds with complex histories. Our bias is toward flashy, fast threats, the asteroids that zip across our orbit. Bernardinelli-Bernstein exposes the danger of slow threats, the giants that move with glacial patience from realms we do not survey, that can be misfiled and overlooked until they're already deep inside our defences. The scariest risk of all may be the misfiled object, the threat hiding under a harmless label in our own databases. This demands scientific humility, which is not a weakness but the highest form of intellectual honesty. Admitting we don't know is the first step toward knowing. Bernardinelli-Bernstein has been a masterclass in humility. It has shown us that the outer solar system is not a static, empty museum, but a dynamic, poorly lit warehouse containing who knows what. The future, however, is bright with discovery. Better telescopes, AI-powered data mining, the Rubin Observatory, the James Webb Space Telescope. All will unveil more secrets. We will find more Bernardinelli-Bernsteins. Some will be larger, some stranger. Each will teach us. But we must heed the cost of assumptions. Assumptions create blind spots. In planetary defense, assumptions can be fatal. We assumed slow-moving equaled harmless. We were wrong. We must now question every classification, verify every orbit, treat every distant speck as potentially significant until proven otherwise. The final, profound thought is this: the universe does not hide. It is not malicious or secretive. Every object is there, obeying physics, reflecting light. The information is broadcast freely. Bernardinelli-Bernstein was there all along in the data, waiting. The failure was not of the cosmos, but of our perception, our systems, our categories. The universe doesn't hide, our labels do. If we wish to survive and thrive in a cosmos that contains frozen continents adrift in the dark, we must learn to see past our own filing cabinets. We must look with fresh eyes, question our assumptions, and embrace the terrifying, wonderful complexity of what is actually there. Because the next Bernardinelli-Bernstein might already be in the data, its pixelated signal waiting patiently in some archive, already falling toward us, and we won't know until someone decides to look.